All right, so remember, we are now looking at like a population percentage. So there's a couple things we can do. Basically, the main equations that we're going to focus on going back and forth with. Let me just get back to it. It was I need to make this like my Algebra 1 book where the pages before were the notes, not. Basically, you're looking at the NP is greater than or equal to 10, and the N1 minus P is also greater than or equal to 10. We have to keep that in mind. But then there was one problem. There it is. We have to realize if we have okay, so that was the equation. This is going to find us a standard deviation. So first one says on page 79, assume 83% of the adult population in the United States drinks coffee regularly. Cheers to that. Oh, that's good coffee. A new coffee chain is opening up, and they wish to conduct a survey to determine their expected business. They randomly survey 50 people from the population at large. Would this method ensure a sampling distribution that is normal? Okay, so problem number one, they are picking 50 random people. Okay, so right now this is greater than the 30, so this is checking off at that point. Okay, but we have to be careful here. So this was 2 sections ago, but now we need to take a look at this. Okay, we know that 83% or 0.83 drink coffee. Okay, so now we have the N and we have the P that works on both of these. Both of these equations now also have to work because we're dealing with a population. Okay, so if I go 50 times 0.83, we want to know if that's greater than 10. And I also want to go 50 minus 1 minus 0.83. And we want to know that that's also greater than or equal to 10. And can someone go 50 times 0.83 on their calculator for me, please? Or on your phone calculator or whatever your method is. 50 times 0.83. Anybody? 41.5. This is 41.5? Okay, so this one checks on the top one. Okay, on this bottom one, this is going to be the same thing as 50 times 0.17. What is 50 times 0.17? $8.5. All right. So this is a no. So friends, we cannot use this as a normal distribution because it failed this test here. Okay? It wasn't a value bigger than 10. Okay, so you kind of keep that in mind. We have a random sample, that's great. A random sample is greater than 30. Great, we're starting to look like we're doing a normal distribution. Now we have 2 more tests that are in place to verify if the normal distribution is going to work, which is the number of people times the percent. If that's greater than 10, awesome, that's working. And then we're going to go N parentheses 1 minus P. And if that's greater than 10, that also works. If any of those fail, it takes away that normal distribution. Okay? So then problem number 2 says we want to find the mean. And the mean we already know. The mean is 0.83. But then we want to find the standard error. Okay? That's going to be this equation here. Okay, and I don't think I made that clear enough yesterday, and I apologize. I failed you. Okay, so, whoops. Get away, go away, go away, go away. There we go. All right, so I have P, my probability, 0.83, minus 1 minus 1 times 0.83, all divided by n. N was the 50 people. So I can find my standard error to be, if I do that math, if I go 0.83 times 0.17 divided by 50, take the square root of that, I wind up getting 0.053. So this is now my standard deviation or my standard error. So I can easily make my normal distribution based on this for number 3. I can say 0.83 is here, and then this is plus 0.053 plus another 0.053. This is minus a 0.0, so plus and plus, minus 0.053, minus 0.053, and it keeps going. Okay? So that changes the standard error. Using the so number 4, using the 68, 95, 97 rule, what captures the middle 95%? Okay, so this is the middle 95%. Okay, so 0.053, let's see, 0.083 plus 0.053 plus 0.053. That's going to give me 9, carry the 1, that's 9, 14, 19. So I'm going to go, oh wait, I'm off there. Did I do my math right? I didn't. Stirrup, you can't take this cat anywhere. This is going to make everything wrong. This should have been 0.83 here, I'm sorry. All right, so that's going to give me 6. That's going to give me 13, carry the 1. That's going to give me that, so 0.93. So this value here is 0.936. Okay? And then I want to find this value here, so I'm going to go 0.83 minus 0.053. That's 7, that's a 2, that's a 7, that's a 7. Then I'm going to take another 0.053 away from that. So that's going to be a 4, a 2, 0.724. So that's 0.724. So that means that 95% of my data is going to fall between 0.724 and 0.936. Okay, if the sample is increased from 50 to 100, explain what happens to the mean. Okay, the mean isn't going to change as we add more and more standard people. Okay, number 6, assume the random sample is chosen from one of the immediate area around the new chain stores. Name an advantage and a disadvantage of conducting a random sample this way. The advantage is it's easy to do because if you know where the store is, you're going to collect data. The disadvantage is it is not representative of a sample of all future customers if you were opening a chain restaurant. So if you were opening, you found Stirrup's Coffee Place, okay, and it's got the best coffee, and I wanted to know, hey, if I had opened another location, I had one location here in Greenwood Village, I'm going to open another location in Lakewood. If I collected data from the Greenwood Village people, it's not going to be indicative to the people in the Lakewood area. So that would be a poor thing to do. What is the minimum sample size needed to pass these assumptions? Oh, okay. This is a good one. Number 7. So I know that I have n times p is greater than or equal to 10, and I know that I have n times 1 minus p is greater than or equal to 10. So if I wanted to figure out what number of people I would need to take place, I know that this is 0.83, and if I tried to solve this, I'm going to put the n right there. I'm going to multiply or divide each side by 0.83, so that comes out to 10 over 0.83, which n is greater than or equal to 12.05 in this case. And then if I solve this one, remember this is going to give me 0.17 times n is greater than or equal to 10. So if I go 10 divided by 0.17, that's going to give me 58.82. So obviously this number is the larger number I want to stick with. This is the smaller number. This number here, if I had n being 12, it's not going to pass this case. But if I had n being 59 people, it's going to pass both cases. Okay, so that's kind of a different thought process, using a little bit of algebra to solve it. All right. Currently, this is on page 80. Currently, 13% of the population of the United States is a senior citizen. Okay, created a sampling distribution to represent the size 36. Okay, so number 8. They tell us 13%, which is 0.13, is the number we're going to use. We want to find our standard error. Our standard error is going to be our, forgot the equation, top of my head, P1 minus P. 1 minus P over N. Okay, so if we took a sample of 36 people, we want to create a normal distribution on this, so I'm going to find my standard error. I know this is my mean, or my population mean. Standard error, I'm going to go 0.13, 1 minus 0.13, divided by 36. Will somebody, is that 0.87 divided by 36? I think if we plug that in the calculator, 0.13 times 0.87 divided by 36, then take the square root, I'm going to find my standard error is going to be 0.056. And then if I created my normal distribution based on this, so I get 0.13 here, I have plus 0.056, I have plus 0.056, I have minus 0.056, minus 0.056. So do y'all kind of see that this normal curve we keep jumping back to? We're just kind of manipulated a little bit using standard error in this case. And then, so that goes with number 8. Number 9, who is our middle 68%? Okay, so this is our 68% here. So I have 0.13 plus 0.056. So that's going to give me 6, 8. That's my upper limit, 0.186. And if I'm on my lower limit, I'm going to go 0.13 minus 0.056. And that's going to give me roughly 0.07. So this is 0.07. So 68% of our population will fall between these using that standard error. And then how likely is it that you have 36 people that end up with 11% are senior citizens? Okay, so going to our buddies, the Desmos family. I should have invested in Desmos years ago. I would have made myself rich using it. So I'm going to go normal distribution. I have a I have 0.13. I have a standard error of 0.056. So if I hit the plus button, I can see my normal distribution. And how likely is a survey of 36 people? I'm using that standard error in there. Good. That would end up 11% or more that are senior citizens. So 11% is 0.11. So you have roughly a 64% chance that you'd have 11% of your population. If you chose 36 people, you have a 64% chance that those 11 people are seen. I'd say that wrong. If you had 36 people, or you have a 64% chance that 11% of your population of 36 people would be senior citizens. that 11%. Okay, he conducted a survey to senior citizens, percentage that is 2.5 standard deviations below the mean. What is your percentage of your sample who are seniors? 2.5 standard deviations below the mean. All right, I got to do some math here. 2.5. All right, so we did 0.13 minus 0.056 minus 0.056. Oh, thank you very little. Here, if you see her in the hall, let her know to come to class. So I got 0.018. All right, so then I'm going to plug in, this is going to be negative infinity. And I'm going to plug in 0.018. So that's about 2.2% below. So the area underneath the curve, which is that red area, is about 2.2%. Roughly. Does this fail any assumptions for proportions? So basically we have to do the sample of 36 times, oops, cleared all that out, 0.36 times oh shoot, it's 36. I don't have 0.36 people. Times the 0.13. If this is bigger than 10, it passes this stipulation. So is 4.6 bigger than 10? Not this week, right? I'd rather have $10 than $4.68. So it passes. It doesn't pass that one, but does it pass the other one? Just seeing if it did work. Times 0.87. All right, so that one is above. So one's above, one's below, but it has to pass both being greater than 10. So this doesn't pass. Assume you conduct a sample at a local shopping mall at 9 a.m. on a random Monday, selecting random shoppers. Identify two problems in this sampling method. So people shopping at Monday at 9 a.m., I don't think is the vast majority. If you ever gone to the grocery store on the weekend, you realize lots of people are going then. And then you're missing the weekend shoppers for your sample space, so things like that might be some errors. And then assume your random sample is 36 adults, produce 10 seniors, identify both P and P hat. Okay, we could do that. Go back to this. All right, so number 14, if you have 36 adults and you have 10 that had 10 senior citizens, okay, so our P is going to be 10 out of 36. Somebody divide that out on a calculator. Tell me what you get, please. 10 divided by 36. 0.2. Ooh, okay. I'm off. Why am I off? Oh, that was P hat. All right, so our P value, I have an answer here, but I can't remember why I got this answer here. I have an answer of 0.13. Why did I get an answer that? Go back a couple slides. No, it's not going to be there. There. Go back to 5.4. So 5-5. P is a population proportion sample proportion. Oh, duh. Okay. So this came from the original problem of the known population of 13% were old folks. Okay? All right, so if you're here, I'm putting the points in for you. Trying to get you guys to buy in still. Finishing up strong, but I know I'm losing more and more of you. All right, friends. Today is Tuesday, is this correct? Yes. Okay. All right, I am on page 13. Page 13 of your notes. All right. We're going to get into something called the confidence interval. Okay. Think of a confidence interval as this. Do you think, being that we have the Super Bowl coming up, regardless of which team you want to win or lose, I don't care, do you think that somebody could run statistics on the game and figure out the probability that a game would be won? But if they were to do that, in order to protect themselves, they could say, hey, I feel 80% confident that Team A is going to win. What does that mean? If I feel only confident. Okay? Confidence interval is a way of estimating a population parameter that incorporates the margin of error. The goal with a confidence interval is to capture the parameter with a high confidence. So remember, the parameter is something that we know about where it's at, but we don't know exactly where it's at all the time. So example 1, let's assume medical researchers are trying to estimate the average cholesterol level of women in the United States. As always, they collect a sample of U.S. women, a random U.S. women that they might use data to produce a 95% confidence interval as follows. Okay, so let's say they're using a 95% confidence interval in this case. So what they're going to say is, hey, we feel, based on our data, that our parameter, our mean of the entire population is somewhere between 156 and 196 as far as the cholesterol. We feel we are 95% confident that our mean is going to fall within there. So think about what this is doing. Okay, you have a 196 up here. You have a 156 down here because plus or minus. I feel 95% confident that my mean, these reds are the mean. So I feel 95% confident that my mean is going to fall somewhere in between there. Okay? So am I 100% confident? I'm kind of protecting myself. Okay? So there are certain things that take place. Now, this kind of stuff gets exploited like crazy. Okay? So let's say I came out with a new vitamin. We got Vitamin Stirrup on the market. You with me so far? This Vitamin Stirrup will guarantee hair growth. This is sounding like a pretty good vitamin Stirrup needs to invent, because Stirrup went from a 4-head to a 26-head. I mean, it's 4. Okay? Okay, I got Vitamin Stirrup. It's going to develop hair growth. Now, if I said I was 80% confident that this is going to grow hair, does that leave me some wiggle room that I might be wrong? So you see how I'm kind of trying to protect myself? Like, I want to sell this hair growth product because I know there's a whole bunch of bald people out there, including myself. Okay? You all have beautiful hair. I hope you all keep your hair. by you taking vitamin stirrup, I'm 80% confident you're going to keep your hair. Okay? But I'm trying to protect myself. I don't want to get sued. Okay? So there's certain variables out there that I'm not sure about taking place. Okay, so we interpret this particular situation here about the women. We are 95% confident that the average cholesterol level of all U.S. women is between 156 and 196. So we're 95% confident. Okay? Now, there's certain confidence intervals that I don't want to have take place. I don't want to go get on Southwest Airlines and fly someplace and have the pilot say, I'm 95% confident that we're not going to crash. I'm not feeling too good about that. Okay? I don't like this 5% wiggle room. Okay? Yeah, if Southwest Airlines starts advertising, hey, 95% of our flights won't crash. I don't know. There's an awful lot of Southwest flights every day. And if only 95% of them make them safely, I don't like this 5% barrier. This isn't good. So we need to figure out a way that we can increase our confidence interval. Okay, in the confidence interval on this situation about the cholesterol, 176 is called a point of estimate and is our best single estimate of the population parameter. So the 176 is our best estimate of the parameter or the mean that's taking place with the entire population. Okay, the average cholesterol of U.S. women. Okay, so the margin of error is 20. That is, we are 95% that our point of estimate, our mean that we're trying to figure out, our parameter, is accurate within 20 points. Okay, so friends, if we found by doing more and more extensive survey that we found the average cholesterol level, the parameter we reached is 157. Did we hit our mark? We did. The person who's running the thing says, we're 95% confident it falls between here. With extension of a big old survey, they did a census. Part of this U.S. Census in 2030 is actually taking a blood sample, checking the cholesterol level of women. I know it's not really. But then they find, hey, we found it's 157. And the guy did this, like, dude, nailed the mark. It's like, you got wiggle room. You got a lot of wiggle room. I mean, you're barely above. It doesn't matter. I told you, I was 95% confident it was falling between those. Yeah, but you only got 157. Now you get people who are arguing the dynamics of statistics. People who are arguing don't really understand it. If you got 157, if you were able to find that, you hit your mark. You did what you wanted to do. Okay? So the margin of error is 20. Okay, we already said that. So the 156 to 196 is called the confidence interval. This utilizes interval notation from algebra and calculus to suggest with 95% confidence the actual cholesterol level of U.S. women is between 156 and 196. We will learn the mathematical procedure for this doing later. Okay, next thing below the dotted line says researcher sets a confidence interval if the researcher wants to create a confidence interval in which they're almost certain to capture the population parameter. They might choose a confidence level of 99% or higher. Okay, such intervals tend to be very wide, so the precision is often very lost. Okay, so what that means, this is a 95% confidence interval. I'm going to pick hot pink. Okay, hot pink. If I wanted a 99% confidence interval, this becomes a lot wider. Okay? So just because I'm more confident doesn't mean I actually know where the heck my parameter is. I mean, this 99% parameter might be between 100 and 300 for cholesterol level. Okay? So if I change my confidence interval, I choose a wider portion of my normal distribution curve that I feel comfortable to say, hey, you want to know something? I'm 99% confident that the lowest grade in my statistics classes will be above a 40%. Does that sound like a pretty good gig? Okay, that's pretty wide though. Okay, now I could say with 40% confidence that I will have more than 10 A's between my two statistics classes. Okay. So researcher sets a confidence interval. Research wants to create a confidence interval which most certain to capture a population parameter. They might choose a confidence level of 99% or higher. Such intervals tend to be very wide, so precision is often lost. Lower confidence levels, such as 90% or even 80%, will be more precise. So the slower my confidence interval, the closer and closer and closer to the normal distribution mean I would get to. Okay, in the example regarding the average cholesterol of U.S. women, the confidence level was set at 95%. Had the research level set to 99%, the margin of error would have increased and the confidence level would have been a lot wider, like I had done with the pink. Okay, let's assume that this is on the next page, page 14. Let's assume that the owner of a major store chain wants to know the percentage of people who enter the store who make a purchase. The owner wants a 90% confidence interval and collects data as needed. The results of this person's test is 0.56 plus or minus 0.05, which is basically this as a confidence interval. Okay, and they said that this person is 90% sure that people are going to fall within that. The point of estimate is 0.56. This means our best estimate is 56% of all customers who enter the store buy something. The margin of error is 0.05. So that means 90% confidence. We believe our estimate of 56% is accurate within 5%. Okay. During election years, you see this all the time. They collect data randomly somehow, and they will say, hey, this person has, this candidate is leading the polls plus or minus this percent. Okay, that's your confidence interval. The margin error, okay, we just did that. Confidence interval is 0.51 to 0.61. This means that we are 90% confident that an actual percent customers who enter the store, someone will buy something, is between 51 and 61%. It needs to be noted that the confidence intervals can provide powerful statistical evidence. If someone were to argue that less than half of the customers who entered the store were buying something, our interval has solid evidence to counter that. After all, the entire interval is above 50%. On the other hand, okay, so being this is above 50%, they're claiming that more than 50% of the people that enter the store are going to purchase something. On the other hand, if we want to make our claim that 60% or more customers bought something, we don't have evidence to contradict that. Okay, if we wanted to say 60%, this is my top end bound. I'm not sure. Okay, when we calculate such statistical evidence, it isn't appropriate to draw judgments based on how close the value might be to the edge of the interval. Okay, we did that last example. Someone might try to argue that the interval provides evidence less than 60% of the customers who entered the store buy something because most of the interval is below 60%. This logic is faulty, however. At a standard of confidence we choose, every value within the interval must be considered plausible. Every value outside the interval would be considered very unlikely, but not impossible. So, this is new. It's a confidence interval. This is a way that you're protecting your statistics based on a thought. Okay? So, I would think, let's have page 81 and 82 due at the end of the period tomorrow. Okay? This, friends, will be on Thursday a quiz of 5-1 to 5-5. Okay? Good? Happy?